Howdy. This picture here shows the current data center structure. In this system, electronic switches compute the next hop for each packet. How do you feel about it? Pretty complex, right? In fact, today's data centers face many restrictions. Capacity is growing faster than Moore's law, which means we not only need to upgrade hardware, but also keep expanding the scale. That brings rising complexity, high power consumption, and more network congestion. So our goal is to step away from traditional architectures and design a brand new solution. While others are building better cars, we are building an entire railway system. So we designed Sirius. It's an optical-based network. Every server in it can receive a laser with a wavelength. Each server emits laser beams, which are automatically routed to the corresponding path based on their wavelengths. Low cost, low power, low latency. And we've already fully implemented our design from hardware to protocols to system integration at a commercial level. How we did this? Let's look at our core technologies. Hardware-wise, there are two key parts. First, the AWGR, Array Waveguide Grating Router. You can think of it like optical dispersion. Light of different wavelengths is automatically directed to different paths. It's fully passive, so it needs no power. With no moving parts, it adds zero switching delay, and now we can make AWGRs with hundreds of ports to handle hundreds of laser beams at once. Second is our laser generator. Traditional lasers change wavelengths by adjusting current, which is slow. But to quickly switch connections between servers, we need fast wavelength switching. So we generate all wavelengths at once, split them with the AWGR, and put a switch on each optical path. We just need to turn on a switch to output its wavelengths. This benefit is huge. Stabilizing current takes 14 nanoseconds, and controlling the switch takes only 0.9 nanoseconds. It's nanosecond level latency, low latency. Architecture-wise, the key idea is replacing logic control with timing coordination since the system is passive. First, it's a flat design, no multi-level AWGRs. To scale up, you just need to buy more hardware, no need to redesign the whole system. Second, since each server only has a few lasers, we use fast time slot rotation to ensure frequent connections. We also add an external clock line to synchronize the system and let each server cache link delays to compensate for hardware differences and speed up coordination. Third, data is sent over two hop paths. Each time, the sender randomly picks a relay node and sets up a confirmation before sending. The randomness helps balance the load. We've shown it reduces congestion, avoids packet loss, and cuts down latency. In the end, we fully built and ran this system. At a scale of 4,800 servers, Sirius achieves 75% less power use, over 50% lower cost per GBAPS, and 75% lower latency under load. And thanks to its flat design, the bigger the scale, the better the gains. So this is our work. In a time trapped by power and chips, Sirius is a breakthrough, a shift from electronic to optical, a shift from milliseconds to nanoseconds. And today, it's ready for real data centers. Thank you.